Hello everyone, and welcome to this presentation by MCAD Technologies and myself, Benjamin Collins, a certified expert here with MCAD and an applications engineer. We're going to talk today about simulation and mesh refinement techniques, what I'm calling rules to sim by. Right? Now, of course, whenever we're simming our various products, we need to make sure that our mesh is accurate for the results that we're trying to get. Now, there's three types of meshes that we're going to go over briefly on the main two on solid and shell meshes today, and then I'll just discuss briefly beam meshes. But basically, a solid beam or a solid element in SolidWorks is a tetrahedral element that has four sides and those 1, 2, 3, 4 points there to provide degrees of freedom on. You can see it's a 3D element, and it's going to bend and squish along those lines. A shell is going to be the same idea, but in a 2D shape. And then a beam is kind of a special case of a shell, where because we know that, for example, an I-beam is prismatic, is the same along one axis, we can kind of represent it as a series of hockey pucks or Oreos or anything like that, and stack those up. As long as those pucks have the same area moments, then the result should be the same as far as a beam diagram is concerned. But taking a look at mesh density, one of the first mistakes that users will make when they're doing a simulation is starting out too complicated. We've all heard of the acronym KISS, keep it simple, stupid. But where this applies to simulation is keeping our mesh simple to begin with. Using what's called a draft quality mesh and keeping it very coarse will ensure that the simulation will solve relatively quickly when we go to run it. But take care in noticing that these won't be accurate results. What we're doing here is testing to make sure that the setup for our simulation is correct, that we've made sure all the parts are restrained, that we've applied materials to everything. We don't want to have to wait for the mesh to solve, and in an advanced sim that could take 15, 20 minutes just to find out that something wasn't properly restrained. So we'll start with this draft quality mesh until we nail down that the rest of our simulation is okay. And then we can start to dial up the mesh quality. Now, when we're looking at mesh qualities, let's take a look here back in SolidWorks. Just to kind of start out, here's our basic shapes of what kind of meshes we've got. So it's a tetrahedral there on the left with a 2D shell in the middle and then a beam element right there. Kind of some simple illustrations. If we take a look at this piece here, a common actually, if we take a look at this next piece over, we've got this beam here. And so like I said, we can look at the mesh quality for this. And what I've done here is to find a mesh quality plot. You can see this is a pretty coarse mesh. There's not very many tetrahedrons representing this shape. And that comes out in the results. If we take a look at this, we can see that, we do get a progression of force. That kind of makes sense. But for the trained eye, we'll notice that we're missing the neutral bending plane here through the middle. The top of this member should be in tension, and the bottom should be in compression, but we're not seeing that switch from top to bottom. And that's because, as we saw in the mesh quality, the elements are spanning across where that neutral bending plane would be. Now, just a brief discussion on how to set up draft quality elements, then we'll talk about what they actually are. So when you're creating your mesh, we can control the size of our mesh elements here. I happen to know this is a 1x1 bar here, so I just set the mesh size at that. But a draft quality element, if we take a look at these shapes here, or even go back to our tetrahedral element here, a high quality element is going to have these 4 nodes in the corners, as well as pivot points or elbows right here at the halfways on these faces. And basically what that lets the tetrahedron do is squish or contort. A draft quality element doesn't have that extra degree of freedom right there. And so all they can do is kind of tumble to the side, right? And fall over. They can't really be squished. Now that makes it much simpler on the computational side, but obviously decreases the accuracy. So when I come over here to my static simulation, I take a look at these draft quality elements, I can see that reflected in my results. So let's take a look at just a quick example. The same size elements, but in this case, I actually just changed them so that they're high quality elements, meaning they have those pivot points in the center, and we can see immediately that the quality of our results improves. We can see the two tension and compression zones as well as the neutral bending plane. And we can see that our results have changed as well. This is going to be important. The fact that when we change our mesh, the results change. We'll talk about that in a minute. All right. Now this is still by no means an accurate result, but we can see that we're getting more close to the real thing here. So let's jump back to presentation here and just get a good rule of thumb or a rule of symbi. All right. Whenever you have a solid element situation, through any thickness, you want at least two elements, like you see here, so that we can get an accurate neutral bending plane, and we can have an element that is purely in tension or purely in compression, and doesn't have to worry about trying to bridge the gap. So we should always have at least two elements through the thickness. Now you can see here on this shape, that's relatively easy to do. But if I were to switch to a different model, say this C-channel beam here, you can see it's relatively long and relatively thin, which means to generate a proper mesh for it based on these criteria, we're going to have a lot of elements, which means a lot of degrees of freedom, which means our solve time is going to go up. All right, so you can see here I've got the appropriate number of elements. However, as we zoom out, oh boy, that's quite a few. So this is where we're going to start to get into mesh control, as well as some of the other mesh types. So one thing we could do in this type of a situation is apply a mesh control. Or if we look back at a different model here, this one right here, we can use mesh controls to refine local areas. So if I have this turned off, and we crashed the program, what would happen there is if I have this turned off, what we're going to see is a mesh type that's much more this density. And it'll be uniform across the part. And the trick to this is going to be that, if I want to have higher accuracy like I do here, it's going to have to be everywhere else as well. So this is where we use mesh control. And we can select either faces, edges, or points to define a region where I'd like a little extra control, but just in that area. And so you can define a particular refinement for that area, as well as a growth size back to what the global value was. So right here I say that, okay, every cell past this face can grow 1.5 times until it gets back to whatever the global value was. This lets me keep some local density rather than trying to mesh the entire part like we saw here. I could maybe give a little local density right here in the corners, through this middle face, something like that, to try and give myself a little bit less to show. All right. So while SolidWorks is restarting here, I'm sure none of you have ever had a crash. Let's take a look at some more details here about what we can do with mesh refinement. So another thing that will happen when we're meshing and our mesh is too coarse, all right, is we can get elements that are very squished like this, or what we call a large aspect ratio, because it's trying to get up in a corner and define the shape of the model. But this means that we're going to lose a lot of accuracy. So one thing we can do here is right-click on our mesh and create a mesh plot to show us the aspect ratios of the mesh that we've created. And what we'd like to do is try and keep that ratio below 3, at least 95% of the model. And what this will do for us is make sure that our elements here are accurate, that they're modeling correctly, all right? So we can use that mesh quality plot to determine that, and I'll show that in a second again while SolidWorks is restarting here. But another element here is to use what's called the Jacobian check, another mesh plot type, to see how our corners are looking. So this is kind of a more coarse mesh. This is also using a standard mesh type. And this is a more refined mesh using a curvature-based mesh. All right. So the Jacobian check is going to tell us, how nicely this corner transitions. And the way we get that nice transition is using a curvature-based mesh, which, as you can see here, will attempt to get a certain number of elements around the corner rather than just kind of haphazardly recreating the corner. It'll actually try and faithfully reproduce that edge there, that circular edge. All right, let's see how SolidWorks is doing as far as getting restarted here. All right, so we've got our parts here. And once again, let's add simulation back in and take a look at this part here, and we can see the refined mesh as well as the use of the curvature mesh here in the corner. One more second just to let it start up here. All right, great. We'll take a look at our mesh plot here. So you can see that with that curvature control, or with that mesh control, we get a lot of nice density here around the corner, as well as only local density, showing us an area that we're interested in specifically. All right, showing the aspect ratio plot here. You can see here I've limited the plot to elements that are 3 or below, but if I loosen it up a bit, you can see that in general we're pretty good. If I shrink it back down to 3, a large number of the elements are within tolerance, but we may actually even want to increase the mesh a little bit. We can see that some of them are pretty squished. All right. If I take a look at my Jacobian plot here, I want to try and keep 6 to 8 elements going around the corner and keep this as close to 1 as possible. All right. So you can see there this looks pretty good. As far as the Jacobian is concerned, we may need to increase the density just a little bit to deal with some of these aspect ratio problems. All right. And again, to create that type of mesh, we can come into our mesh controls here, and under our mesh parameters, change it from a standard mesh to either a curvature or a blended curvature base. Blended curvature is new for 2016. It just kind of tries to create a more seamless transition there, but can't be used with adaptive meshes, so be careful about that. We can use a curvature-based mesh here, and down here we can define how many elements we'd like to be able to go around a corner, minimum, right? So I say, okay, no matter how small it is, we have to have at least 8 elements going around a corner, and that'll define the minimum mesh size as well to try and gather our density there. All right, so keeping those corners nice and smooth, nicely represented. All right, now we talked earlier about shell meshes, and there's always a question of when do I shell and why do I shell and how do I shell, all right? So here's a good rule to sim by as well. Solid elements are used for parts with low aspect ratios, just kind of a height to a thickness, right? And if your height to your thickness is like 1 to 5, it's relatively square and thick like this, right? Then we should be using tetrahedral solid 3D meshes, right? As we get towards really thin and long parts, right, like plates and sheet metal pieces generally, we need to start thinking about shell meshes. All right? There's 2 types of shell meshes, thick and thin shell meshes. And basically the assumption is if you're using a thin mesh, you're only going to be calculating for bending deformation. All right? So the software is not going to account for any shear deformation in the material, where the top of the material moves more than the bottom material and kind of the normal line here would be disturbed, right? So a thick mesh is going to be more accurate for something that's a little thicker, right? It's going to be closer to that 3D tetrahedral, but you still want to be able to use the 2D elements of a shell. The advantage of that is that we can use far fewer elements to represent a shape, because as you can see here, as we get to those smaller ones, here's that problem again. To get 2 elements through the thickness, we need a lot of elements, right? So if we could assume this is 2D, then we can just simply represent this as a few triangles and move on, right? So thick versus thin, just take a look at whether or not you're interested in the shear or just the bending information for that shell. And again, if it's about 5 to 10 thickness ratio, maybe think about thick. They're pretty, in my experience, it's pretty much solid or thin shells, but you might run into a thick. And then obviously as you get into like sheet metal casings and any kind of wide, thin-walled part like a pressure vessel, you're definitely going to want to start using thin shell elements. All right. Finally, let's talk a little bit about convergence. All right, so whenever we're using a simulation, I mentioned that as we change the mesh, all right, as we increase the density in the mesh, we're increasing the degrees of freedom in the model, all right? And what this directly translates to is time needed to solve the model, all right? But as we change the mesh density, you'll notice that your results change, but they'll slowly stop changing, all right, as we converge on the real value. So what we'd like to see is start out with a draft quality mesh down here. Quick and dirty, runs fast, lets us know if our simulation is running correctly. Then start to increase the degrees of freedom and see if you can find where your information is leveling out, right? And as soon as it stops changing by 5 to 10%, we consider that converged, depending on the accuracy you need. And really, this is a balance between the accuracy you need versus the time it takes to solve this. One thing we want to be careful about is if we take a look back at this simulation, where I showed you the high quality elements, we notice that there's a high stress continuity back here in the corner. And this is kind of what we expect based on the loading conditions. I basically glued this back wall to an imaginary wall over here. And that's kind of an inaccurate constraint, right? And so what we've got here is a singularity, a stress singularity is what they're called. And so even as I continue to increase the mesh, what I'll start to see is an ever sharper set of stresses right here in the corner. Because there's sharp corners on the model right here and it's fixed to the wall, this corner is just going to get more and more and more and more stressed as we refine the mesh. It's a singularity, it goes off to infinity. So we need to be careful about looking at things like that and also realize when we have a stress singularity and kind of ways to look around it maybe. So let's take the mesh up on this one a little bit. And let's just get the mesh up to, let's go 1/8 of an inch, right? Just to give us some more accuracy. Runs more on the fine side. So we can see initially the mesh is a lot more dense, that's nice. Gives us a lot more accuracy. The first one of these solved near instantly. You can see this one takes a few seconds, but it's still pretty quick. All right. Now if you take a look at this, something is weird, right? Most of the part is blue, and yet the scale is going off the chart here. What's happening is right here in this corner, we're getting a stress singularity. All right? So two ways you can look at this. One is to attempt to remodel this part. Maybe this is a simplification we've made on our model, and maybe there's some detail we're missing there, maybe a fillet or a load-bearing piece, right? That's going to take some of that force and transition it smoothly. The other thing we can do is take a look at the scale on this chart here. If I set this value closer to what the yield strength is of the part, I can begin to see a more accurate representation of the stress in this part. And so I could see initially that that high stress value was really centered down there in the corner. And so now I can see that anything red or worse, basically, has yielded, right? So I can say, okay, well, we're really yielding the top and the bottom here. In most cases, this is enough to say, okay, we need to rework this, right? We broke it up here and down here. The other option we can do is to use what's called a section clipping or an isoclipping. And isoclipping is pretty cool where we can set this value to a particular size, right? Let's say we set this to the yield strength of 2.575 or 757. 7. All right. Now what this is doing is the software is only displaying cells or elements that are at that value or less, right? So what we can do is kind of determine what is the degree that we're seeing here that stress singularity is taking its toll, right? So if I go back and do another ISO clipping, I've just increased the scale back to its full amount. And what I can do is kind of pull this down and see that, like, for a long time, we really don't lose any information out of the corners. And that's because of how highly concentrated that stress singularity is. So this might be enough for you to, begin to ignore that stress singularity if this is kind of a simple run of your simulation and you just want to see kind of the overall results. But definitely take a look at that. Use this ISO clipping and use section clipping as well. Similar idea where we can kind of see cutting through the plane what our values are. Use these ideas to help you analyze your results and see if it really makes sense. Simulation is a very powerful tool, but it can never take away from your inherent skill as a designer to look at it and say, that doesn't look like it makes sense, right? Otherwise, we'd all be out of jobs. So let's hope they don't figure that out too soon. All right. So we're using all this idea to get to convergence and get the accurate result in our model, and watching out for stress singularities along the way. Now, one method we can use to get to our convergence is to just manually increase the mesh size. But SOLIDWORKS also offers us the ability to use H and P adaptive meshes in the attempt to find convergence, all right? And what these two systems do is increase flexibility, basically, to try and more accurately model the flexibility of the real part. Now, an H-adaptive mesh is going to take elements that are highly inaccurate or have a high aspect ratio, like we talked about earlier, and break them down into smaller elements so that they're a little more accurate, right? And it's going to do multiple passes of this, checking based on an accuracy value that you set. All right, now a P-adaptive mesh is a little different. We talked earlier about this would be a standard tetrahedral mesh where it has nodes on the corners, as well as elbows in the middle of the edges that allow it to bend and kink. This makes it what's called a second order element, where we have two bending pieces along this line, right? It makes it a second order element. A draft quality element is actually just one line here, right? It doesn't have this bending piece. What a P-adaptive mesh will do is increase the number of points along this line up to 5 bending elements to give that triangle more flexibility to be able to crunch and squeeze and model, right? And again, the software is going to go through and do passes to increase the flexibility as needed to increase the accuracy. Now, how do you use, which one do you use these for and when? That's a more in-depth discussion that we can delve into in another video. But I just wanted to kind of introduce the idea that all of these tools are available to you and why they're important. All right. Now, thanks for watching for the moment, and if you have any questions, please feel free to get in touch with us. My email is just the same as the support at MCAD, just Benjamin@MCAD. And as you work with your simulations, play with some of these tools. I encourage people to doodle, if you will, and make a model, or make a model that you had physically tested and you know the results for, and try and match it using these techniques and using these different element types to match up with the real world results. All right. So again, thanks for watching, and we'll see you next time.